Let us continue with the section of electric flux. Okay, electric flux. Later on I will explain again once more what is the electric flux. So, what is the electric flux? Actually, it is a physical quantity and it is a number. It is a scalar quantity, means it is a number along with the unit. With what is the unit? Newtons per coulomb meter. Okay, newtons or Weber. What is the SI unit of electric flux? Electric flux phi is equals to delta pi is equals to E bar dot delta S bar. Okay, it is a scalar product of E bar and delta S bar. Delta S bar is the area vector. E bar is the electric field. So, in a field E bar, an element, area element is kept. The number of field lines are crossing it. If there is an electric field, there are the electric field lines, okay, in the space. The number of field lines crossing this particular area element delta S is given by a number. That number is what? Delta pi, called electric flux. It is equals to E bar dot delta S bar. That's equals to E into delta S into cos theta, because E bar dot B bar is AB cos theta. Okay. What is this theta? Theta is actually this delta S bar is having the direction. So it is in the direction of what? Normal to the surface. This is the surface. Say this is the field E bar. So that also represents the field lines. Okay. So this is the element delta S, surface area element delta S element. A page of a paper is an element, surface area element. Okay. But the direction of the area element normal to the surface. So this is the surface and the direction of this surface element is normal, perpendicular to the surface. So this is delta S bar actually. Okay. Theta is the angle between the field E bar and delta S bar. So number of this actually electric flux represents, it is the scalar product of the field E bar. If this element is kept in a field E, actually electric field means if there is an electric field in the space, there are the electric field lines. Okay. So the electric field lines is cutting this or crossing this particular area element. Then the number of electric field lines crossing this area element can be calculated by is represented by a number delta pi. That's called flux. Flux through the what it is area element is equals to E bar dot delta S bar. That's equals to E into delta S into cos theta. So SI unit is E is in newtons per coulomb and delta S means area per meter square. Okay. So that is area unit of flux, also called Weber. Okay. In current electricity it is taken as Weber, but here in electric field case it is denoted by the SI unit is newtons per coulomb per meter square. Newtons per coulomb meter square. In current electricity, the flux is represented by the unit Weber, and the same both are. So this delta pi is a number. That number is proportional to the number of electric field lines, crossing this particular area element. Actually, delta pi is exactly not equal to the number of field lines crossing this particular area element. Delta pi is proportional to, suppose delta pi is 100. The number of field lines crossing it may be proportional to 100, 100 or 200 or 300 or 400 like that. Okay. So, or 450 means proportional. So, number of field lines is proportional to delta pi. Therefore, number of field lines is equal to k into delta pi. Suppose k is 4.5, delta pi is 100, then it is 4.5 into 100, that's equals to 450, like that. So, what is that k? What is the how many number of field lines are crossing the area element is immaterial, not necessary also. But that figure is this delta pi electric flux is a figure that simply represents what it is, number of field lines crossing that particular area element, and that area element is kept in an electric field E of a certain configuration of charges. Okay. There are configuration of charges, then only around it there is an electric field. The electric field are pictorially represented by field lines. Okay. Now coming to the one important, what it is, theorem. On that important theorem, Gauss's law, it is called Gauss's law or Gauss's theorem. So there are three derivations. Actually, one derivation is omitted this here. So two derivations. Among those two derivations, usually they are used to ask one problem, either one problem or theory. Okay, either problem or theory. On these electric field lines, one problem and one theory is sure. On dipole, if theory is asked, and on this what it is, Gauss's theorem, problem will be asked. If on Gauss's theorem theory is asked, then on dipole problem will be asked. Okay, the dipole electric field on equatorial line as well as on the equatorial plane or on the axial plane, problems are there. That problem will be asked. Okay, there are one theory and one problem is sure in this particular topic, and along with that one mass question, two mass questions also will be there. Okay, now coming back to the electric flux. If electric field is uniform, so uniform electric fields are represented by a set of parallel lines. Set of parallel lines indicates the uniform electric field. Uniform electric means strength of the field is same everywhere. Magnitude of the electric field is same everywhere. That is the uniform electric field denoted by the set of parallel lines. Okay. Then electric flux through the surface area S. I have not taken a small area element delta S. I have taken what it is, some considerably large area. Okay, yes. Electric flux through the surface area S is given by pi is equals to E bar dot S bar. Okay, E bar dot S bar, that's equals to E into S into cos theta. Okay, now you can take not delta S bar, you can take even whole surface area only you can take. Okay, this is the surface area. It is made up of what? Small surface area element, each of delta S. Then actually flux through each area will be added to get the flux to the entire area S. Instead of that one, if the field is uniform, actually the flux through this entire area S is the flux through each area element. So in the sum of area, this is delta S1, this is delta S2, this is delta S3, this is delta S4, then flux through this entire surface area S is the flux through delta S1 is delta pi 1 plus delta pi 2 plus delta pi 3 plus delta pi 4 plus delta pi 6, like that. But if the field is uniform, then at once we can work out the electric field through the surface area S. That is nothing but pi is equals to E bar dot S bar, that's equals to S into cos theta. Okay, if the field is uniform, we can work out the electric field through the surface area of considerably large area at once by the same formula, pi is equals to E bar dot S bar instead of delta S bar. Delta S bar means flux to a small area element, a part of this area. This is delta S bar. Okay. If the field is uniform, at once you can work out the total flux passing through this particular area element. That's that area. What area element? Area. This is the area element of this area. Flux through this whole area is equals to E bar dot S bar when it is the field is uniform. Otherwise, how to calculate the flux through this whole area? The field is not uniform. This is delta S1 bar. This area is delta S2 bar. This area is delta S3 bar. Then the whole area is S. Then the flux through this whole area is equals to delta pi. Flux through this one is delta pi 1. This is delta pi 2. Flux through this area element is delta pi 3. Flux through this area element is delta pi 4. Then the total flux pi is equals to delta pi 1 plus delta pi 2 plus delta pi 3, so on up to delta pi n, where delta pi n is what it is, the flux through the area element delta Sn. Okay, but if the field is uniform, at once you can work out the flux through this whole area. That's equals to E bar dot S bar, that's equals to Es into cos theta. This is the number which is proportional to the number of field lines crossing this particular area when this area is kept in an uniform electric field. Okay, now coming to the Gauss's law. What is this Gauss's law? Says that the statement I have given very important for this particular statement, because two derivations are there. While asking the derivation, they are asking this law also stated the Gauss law and prove this particular derivation. Okay, two derivations are there. I will tell you what are those two derivations. First statement of Gauss law will be outside. Gauss's law. Okay, electric flux pi through a closed surface. Mind the closed surface area S. So here is a closed surface area. What is the closed surface area? For example, a closed cylinder. Closed cylinder means all sides are covered actually, okay, no open. Either bottom is open or top is open or the lateral side is open. Okay. So closed surface, okay. So closed cylinder or closed sphere, a football is a closed sphere, okay. So the flux through a closed surface area, yes, is given by pi is equals to q upon epsilon naught. Pi is equals to q upon epsilon naught, where q is the total charge enclosed by the closed surface. Yes. Okay, try to understand this particular simple law. Here is a closed surface. Just imagine a football. Okay, a spherical closed surface and football. So inside that one, but not made up of leather, made up of a metallic conductor. The surface area is made up of a metallic conductor. So this is a sphere. Inside that one, charges are there. Electrical charges are stored. Say one is Q1, another charge is plus Q2, another charge is minus Q3, another charge is minus Q4, another charge is plus Q5, point charges. And the total charge is plus Q1, plus Q2, minus Q3, minus Q4, plus Q5. Know that the charge is a scalar quantity, can be added algebraically. Therefore, net charge or total charge is plus Q1, Q is equals to plus Q1 minus plus Q2 minus Q3 minus Q4 plus Q5. Okay, algebraically charges can be added. Then the flux means the field lines crossing this particular what is closed surface. Just a torch is kept inside the what it is football. Suppose the leather is made up of a transparent material, then light is switch of the torch is on, then light is emitting through all the sides of the football like that. Then light is emitting through all the through all the surface area of that particular transparent material, which is spherical in shape, where torch is kept inside, the light source of light is kept inside what it is, the closed surface of spherical size. Okay, so then like that the charges are there inside the closed surface. Then flux means electric field lines are coming out of that particular closed surface. Then how much electric field lines means how much flux is passing. Electric field lines and flux are actually not exactly same, but electric field lines is proportional to pi. Okay, so electric field lines are means flux crossing this particular closed surface is given by q upon epsilon naught. That is the statement. So then total charge q is equals to q1 plus q2 plus q3 minus q4 plus q5. Then the pi, number of field lines crossing this particular what it is closed surface, pi is equals to, just like light is emitting from the transparent surface of the sphere when the torch is kept inside the sphere. Okay, like the flux is crossing. Then how much the flux is crossing? Given by pi is equals to q upon epsilon naught, where q is the net charge, is total charge inside the surface. It should be inside, not outside charge if we consider. Outside charge q6 is there, then q is not equals to plus q6. Only inside charge are to be taken. Okay, where q is the total charge enclosed, not outside charge should be considered. Outside the closed surface should not be taken. Enclosed inside only by the closed surface. Yes. Okay. So some note regarding that one is, for example, if q1 plus q1 minus q2 minus q3, so on qn are point charges enclosed by a closed surface S. Then net charge q is equals to, what is the total charge? Net charge plus q1 is positive, q2 is negative, minus q2 minus q3 plus so on up to plus qn. Nth charge I have taken it as plus. Flux through the closed surface now is pi is equals to net charge divided by epsilon naught. What is epsilon naught? Epsilon naught is the absolute permittivity of the free space. So its value is 8.854 into 10 to the power of 11 SI units. So absolute permittivity. Okay. So look here. Even though the surface area S is there in the Gaussian law, flux is there. Figure number. Physical quantity that represents the number of field lines crossing the surface area. Okay, so is independent of S here. No S is there in the picture, in the expression of the Gaussian law, even though the charge is enclosed by a closed surface of area S. So suppose here is a closed surface of spherical in nature, then S is equals to what is the surface area of a spherical body? 4 pi r square. where r is the radius of the spherical body, or football is a spherical body, and the leathery area is 4 pi r square. The flux crossing this leathery area when a charge is q is kept inside the football is given by pi q upon epsilon, where q is the charge kept inside the football and epsilon is the absolute permittivity of the free space. Even though s is equal to 4 pi r square, in this expression the s does not appear in the expression. Okay, pi is equal to q upon epsilon. Then there are two formulas to work out. What is flux through a closed surface? Flux through a surface. One is pi is equal to E bar dot S bar, another one is by Gauss's law, pi is equal to q upon epsilon. That one only we are doing in the two derivations. In the two derivations, we are working out the electric field due to a charged body using the Gauss's law. Using the Gauss's law, we are working out the field at a point due by a charged body. If there is a charged body, around the charged body in the space, there is an electric field at every point. The field at a point by a symmetrically charged body. A body should be asymmetric in nature. What do you mean by symmetric in nature? The circle is symmetric in nature. A body is said to be symmetric in nature if it is folded on a line. So you are getting two exact parts, two halves you are getting. Then that body is called a symmetric body. If a symmetric body is charged, then I can work out the electric field using the Gauss's theorem. Okay, electric field at a point by using the Gauss's. What is the formula for the electric field at a point? If a body, symmetric body is charged, then electric field at a point can be worked out using the Gauss's law. Okay, two symmetrical body, three are were there actually in the last time, but here one is reduced. So two symmetrical bodies. One is a line is conductor. If a line is charged, okay, a line is charged, a line conductor wire is charged uniformly, then field at any point P in the space can be worked out by the Gauss law. First one, and second one is a metallic plate is charged. Metallic plate is a uniform geometrical figure, no, because it is folded on a what it is, a particular line. You can get two exact halves. Why is also asymmetric? But because it is cut at a point, so then you can get two equal pieces. Okay, so one field at a point due to a uniformly charged wire. Second one is field at a point due to what? Uniformly charged a metallic plate. Okay, these two derivations are there. While deriving those two derivations, that we are calculating the flux by this formula q upon epsilon, and at the same time we are calculating the flux by the same formula E s cos theta. Using and equating both the fluxes, we are getting an expression for the field E bar. That is the intention of what it is, the derivation, getting a field E bar at a point. So we are working out the field, flux. Okay, we are working out the flux pi by the Gauss's law as well as pi by the formula E bar dot S delta S bar. Then we are, this is also flux, this is also flux through the same surface area S. Then what it is, so both will be equated. We are getting an expression for the field E bar. So we have to work out the field E bar due to a symmetrically charged body. Okay, so let us see that one later. Let us consider some what it is nodes. If Q1 plus Q1 minus Q2 minus Q3 so on to Qn are the point charges enclosed by a closed surface S, then net charge Q is equals to Q1 minus Q2 minus Q3 so on plus Qn. Flux through the closed surface pi is equals to Q upon epsilon 2 here plus Q1 minus Q2 plus Q2 minus Q3 so on are there. The charge minus Q2 minus Q3 plus Q1, the charge inside a closed surface. So here is the closed surface, then the flux is electric lines through that particular closed surface is pi. Flux symbol is pi, plus pi indicates the electric field lines, number of electric field lines. That is equals to Q upon epsilon. Some note regarding the Gauss's theorem. The closed surface is called Gaussian surface. This closed surface which encloses the charge Q, Q must be inside that closed surface. This page is not a closed surface. Try to understand what is the closed surface. This is not a closed surface. Suppose this is folded like this from all the sides. Then the space inside it is a closed surface. Okay. then space inside it is a closed space, and this surface is called a closed surface. Okay. Closed surface is this is open. This is not a because open. Suppose this is closed, then the space inside it is a closed space, and this surface is a closed one. From all sides if it is closed. Okay. If charge Q is plus kept inside this particular closed surface, then the flux through this, what it is, closed surface, entire closed surface is given by pi upon epsilon. Okay. So Gaussian surface is called Gaussian surface. The shape and size, mind very important, the shape and size of this surface is immaterial in this particular formula. Pi is equals to Q upon epsilon. The shape may be any shape, not necessarily a regular shape. Okay, not necessarily a regular shape. A closed surface, not necessarily spherical in nature. It may be like this also. It may be any irregular shape, but it should be a closed one. Okay, shape and size of this surface is immaterial because in this formula S is not there. The shape is more, the size is more, then automatically area S will be more. The more flux will be passing through it, not like that. So the shape and the size is not material, only the amount of charge enclosed by it. How much charge it is bounded by that closed surface is important. Okay, for the calculation of the flux pi. Q is important, not S. The shape of the closed surface is also immaterial. It may be a regular shape or it may be an irregular shape. If the net charge Q is positive, the total charge Q is positive, then electric field lines are radially outwards. The field lines are radially outwards. Okay, the field lines are radially outwards. E bar. And radially outwards, and the flux pi is taken positive. In that case, flux A is taken as positive. If the net charge is negative, the net charge Q is equal to Q1 minus Q2, if negative or heavier than the positive, then automatically net charge is negative. Net charge is negative, then the field lines are radially inverse. Then the field lines are what? Radially inverse. Like this, don't show like this, because there is no field lines inside the closed surface. One point I will explain later on. Even though the charges are there inside a closed surface, there is no field lines inside the surface. Only it will be at the surface only. Okay. So the net charge is what? Negative. The field lines are radially inverse, and pi is taken as negative. At the same time, one more point I have not given there. I am simply explaining that point. The position of the charges is not important inside. So wherever it may be positioned, Q1 may be anywhere, Q2 may be anywhere, Q3 may be anywhere. The position of the charges inside the what it is closed surface is not material. Okay, wherever it may be, the charges, point charges may be placed wherever inside the closed surface, but it should be inside. The inside may be at the center, maybe at the clinging to the surfaces, whatever it may be, but that is not material. The position of individual charges inside the closed surface is not material. Okay, total charge only is to be a material in this particular expression. R is equals to Q upon epsilon naught. Okay, these are some points regarding the Gauss's law, and on this law let us take two important derivations one by one. Okay, if time permits, I will simply 30 minutes video it is. Yesterday actually only one video was sent because due to the problem in Wi-Fi. Today I will send 3 videos. Today I will send 3 videos. Actually already 3 videos are sent actually. Okay. Now let us take one derivation. I will explain this derivation. Only 6 minutes is left out. Only 6 minutes. I will try to come before that. So I am not going to explain. The 2 derivations are there. That is the end of this topic. I am not going to explain the derivation today. In the next class I will take. But before that, one more point I will clearing, because that is the important point in the derivation. So again I repeat the repetition. Actually, if the area element, the flux through an area element, so delta S, area element of area delta S is given by delta bar is equals to E bar into delta, what it is, S bar, that is equals to E into delta S cos theta. Okay, where theta is the angle between the field E bar and the normal to the area element, here theta is 0. Why theta is 0? Tell me. The normal is also in the direction of E bar. Normal means perpendicular to the surface is called normal. Okay. The normal is also in this direction. Field is also in this direction. Theta is 0. In this case, I told no. Maximum flux is passing through because cos theta is cos 0 is theta. Theta is the angle between the normal to this surface. Normal means perpendicular to this surface and the field E bar. Angle between the field E bar, direction of the field E bar, and the normal to this surface. Normal and field E bar are coinciding. Therefore, theta is 0 in this case. Then flux through this closed surface when it is kept in a field E bar is means number of field lines crossing this particular surface element is E into delta S, which is the maximum flux. Suppose, so same is the case of what? The flux through area S also. Okay. If the field lines, the SC is what it is kept, the area S is kept perpendicular to the direction of the field. Okay. This is the what it is area S. This is the surface S, and it is kept perpendicular. Perpendicular in the sense this edge and this edge are at 90 degree. No. So therefore, it is kept perpendicular. Then, actually theta in this case, theta is not 90. Theta is not the angle between this edge and the field line, electric field. Okay, theta is not the angle between this edge of the what it is area and the field E bar. Theta is the what? Angle between the normal. Normal is this duster. Normal is perpendicular to this surface. This duster indicates the normal to this surface. Theta is the angle between the normal and the E bar. In this case, normal and E bar are coinciding, coming along the same line. Therefore, theta is 0. In this case, maximum flux is passing through this area element. Then pi is equals to E into S. Okay. If the area element is kept parallel, therefore, if the element area is kept perpendicular. So perpendicular. Look here, 90 degree. Okay. Kept perpendicular. Area is kept perpendicular to the field bar. The flux is maximum. Number of field lines crossing it is maximum. In this case, theta is not 90. This is not the theta. Theta is the angle between the normal. This is the normal. Normal is perpendicular. In the definition of flux, what is the theta actually? Theta is the angle between the normal to this particular area element and the field E bar. Angle between E bar and the normal itself is theta. So even though what it is, the angle between the edge of the area and E bar is 90, this is not to be taken as theta. Angle between the normal and E bar is to be taken as theta. So therefore, if the area element, find one point, if the area element, then later on I am not explaining the derivation, orally I will tell you, casually I will tell you that, but try to remember here only, so try to understand the point here only. If the area element is kept perpendicular to the field, this is the area element, area, it is kept, field is in this direction, field is along the board horizontally, then the area is perpendicular to the direction of the field. It is not, field is in this direction, therefore look at the angle between the area and surface and what it is, the field, 90 degree. In this case, more field lines are crossing it. Okay. If second case, I have taken one more case, if the area element is kept, okay, parallel to the field. If this is the area, this is the not area element, area, full area, and the fields are in this direction. Fields are in the direction of chalk piece, like this, in the direction of my arm. Then in this case, the area is parallel to the field. My arm and surface of this area is parallel. Then no flux is, zero flux is passing through it. Why zero flux is passing through? No field lines is passing through it, cutting through it. Because in this case, what is the theta? Theta is the angle between, this duster is the normal to this surface. Theta is the angle between the normal to this surface. Normal and the perpendicular. This surface is perpendicular draw ಮಾಡಿದೆ. ಮತ್ತು ಇದು ನನ್ನ arm field lines ಇದೆ. My arm is the direction of the field. Okay. So in this case, theta ಏನಾಗುತ್ತೆ? Angle between duster, normal. Duster is the normal to the surface. And my arm is 90 degree. 90 degree ಆಗಲ್ವಾ ಇದೆ? Here is 90 degree. Arm ಮತ್ತು ಇದು normal to this surface. Okay. And so my arm is the direction of the field. Angle between my arm and the duster is 90 degree. Therefore, the flux through it is E into pi is equals to E into S. S is the surface area of this. area work. Okay, E into S into cos theta. Theta is what? 90. Therefore, E into S into cos 90. Cos 90 is what? 0. Therefore, it is equals to 0. Suppose the field is like this, direction of the field is like this, element is kept parallel to it, the area element S is kept parallel to it, then automatically no field